think it's recording. That red usually means recording. Yes. Okay. Thank you. So, okay. So then, let's see, what else? Nope, we've talked about it all. Oh, and so then because I'm going to be out of town, you're going to want to contact Mark with your questions. He's going to have office hours in ECA. I think it's 209, Tuesday and Thursday from 11:30 to 1. You can reach him at mashbr1@asu.edu. So let me write that down really fast. So his email is oh, you want a different one? Mark.a at ASU. Okay, cool. That's easier than the other one. Cool. So if you want, you can contact him with your questions. I should be able to answer emails, but you know, conference internet time is sketchy. So I'll do my best, but if you need immediate, faster responses, you might want to contact him. Okay, so then, in light of the test, right, we want to make sure that we know big picture and details. So the big picture, again, is that, calculus is here to address two problems. You know how much of something there is, and you want to know how fast it's changing, and then you know how fast something is changing, and you want to know how much of it there is. So we've been addressing the second scenario, right? So that is often called integral calculus. If you've got friends taking calculus right now, they probably haven't done that, and they started with the other one. But the cool thing about what we're doing is that we're actually getting some deep meanings out of what we're doing. So this has been our focus. And of course, the way that this has looked for us, is to have a exact rate of change function. Okay. And then our goal is to write an accumulation function. Okay. And the way that we built that up was to define an approximate rate of change function, which we called the step of x, and use that to create an approximate accumulation function by adding up sums, adding up little bits of changes. Okay. And so if we wanted to, again, record this process, we start with our exact rate of change function. That's this guy. We define our approximate rate of change function with our step function. And then we get our approximate accumulation function by adding up all of this. Okay. Now, what was the all of this? Okay. So the all of this was taking the sum of bits of change for all the full intervals between a and x, and that's what's represented on this left-hand term, okay? And then adding up the last little bit of change for the partial interval from left of x to current x, okay? But really what all of these terms are, right? We're adding up a bunch of things here, and then we're adding one last thing over here. But really, the big picture is that we're adding up a whole bunch of rates times changes in x's, okay? Which we know produce changes in y's, okay? So little bits of changes that we're adding up to talk about accumulation. Okay, now because I said we need to know the big picture and all the little details, I'd like to challenge you to see what changes about this accumulation function if we were to use mid of x instead of left of x. So I want you to take a minute, talk to your neighbor, and figure out what do you have to change about our approximate accumulation function if we were to use mid instead of left. You guys want to talk about it together now? Just tell you. So, does anybody have a suggestion for what I should change to make my accumulation function based off of mid-x? Cool. McLean, are you here? So you're looking at the second term, right? Second term? You said r of left of x? You want to change it? So in this term, you want to change r of left x to be r of mid x, okay? And that's because we're taking the rate at the midpoint, right, of every interval, okay? Do I need to change, do I need to change anything in these parentheses? Should I change it to be x minus mid x? I'm hearing a yes and a no. Who wants to argue for their, yeah. Okay. Great. Okay, so remember, this is a rate times a change in x. And the change in x in the last interval still has to start at the beginning of the interval. So it has to go from left of x to current x. So that is our new second term. Do we need to change anything about the expression inside of the summation notation? Yes. Okay. So what's the issue here? We've got rates evaluated at the left endpoints right now. So how can I change this expression so that I'm finding rates evaluated at the midpoint of each of the jth interval? Arian? Okay. So notice if we change the -1 to -1/2, that will actually do it for us. Exactly. Okay, because if you think about it, right, when you plug in j equals 1, then you've got a plus 1/2 delta x, so halfway into your first interval. If you plug in j equals 2, you've got a plus 1.5 delta x, so that'll be halfway through your second interval, et cetera, et cetera. Okay? So this is all the same. Okay? And that's how it would change. Cool? Yeah. So this is representing the change in x in the partial interval, right? And the partial interval still starts at left of x. Remember, when we use the mid of x, we still divide up our intervals. You know, so here's like a, when we divide up our intervals in delta x's, okay, so there's a delta x interval. And then we've got some rate of change function. And then we use the rate at the midpoint, okay, but the interval itself is still like that expanse of delta x, starting at left of x and going to right of x, if you will. Okay? Okay, cool. So that's what I mean when I say you need to know the big picture and you need to know the details. You should be able to analyze every element of this expression. Yes. Inside of, yeah. If we were doing right of x, you would have j delta x there. And what else would have to change? It would have to be right of x here. Okay, great. Super cool. Okay, so then, but that all, of course, was to give us an approximate accumulation function. And we can only be satisfied with that for so long. So we talked about how we could improve our approximate rate of change and our approximate accumulation function by making delta x get really, really, really small. Okay? So when we do that, we end up with this notation. So this integral notation, okay, means exactly the same thing as what we've been talking about. It's just condensed, and it applies when we take delta x to be like atomically small, okay? So just a reminder about the notation. When you look at it, right, the integral symbol itself helps to remind us that we're adding up little bits of accumulation. We start at a, we end at x, and then we have to use a different variable inside of our integral to help us keep track of like the changing inputs. Okay, so once again, when you see this, so I'm writing TA to mean true accumulation. You should think of the right-hand side, the integral notation, as this whole summation expression with extremely small values of delta x. Okay. Does anybody want to ask questions about this so far? So this is what everything that you talked about until Friday. Yeah. Oh, so you're talking about like you saw on the previous slide, instead of TA, it was f of x, capital F of x. It's a convention. It is a really common practice to use capital F when you're introducing an integral. It's just conventional. Okay. Now there is something too, though, like using T of A or F of X instead of just A, because the actual summation notation is A of X. And that is technically a different function, right, than this integral. Okay, right? This one is giving us exact things. This one is giving us approximate things. So they are distinct, and you should label them differently if you're talking about them in the same breath. Okay, because otherwise you're talking about two different things with the same name, and that gets confusing. Question? Okay. All right, so let's practice a little bit. Okay, so for each of these expressions, I want you to determine if the expression that's written is valid. If it is valid, tell me, like, break it down for me. What does it mean? Is it going to produce a function or a value? And then if the expression is invalid, fix it. Okay? So take a few minutes, work with your neighbor if you want, and we'll talk about these together after you think. All right, let's talk about it. So the first one, is it a valid expression or an invalid expression? It's valid, okay. So what kind of thing does it produce? It produces a function. Can you be very specific about what does this function do? What does it tell us about? Too vague. Let's see. Okay, what is this thing in here? That's the exact rate of change function. Okay, so if I wanted to write down what it was, I could say r of x equals x squared minus 3x plus 7, right? or I could use t's, but I could also use x's because that's commonly what we do if I want to graph it, for example. So this is my rate function, and this whole integral is going to give me the exact accumulation function that starts where and ends where. Starts at -5 and ends at x. Okay, so if you were to call this big F of x equals, okay, then if I were to put in f of 1, for instance, what would that tell me? I'm sorry? The endpoint? Okay, so 1 is where we stop accumulating, and so f of 1 would give me the total accumulation from -5 to 1. Super cool. Do we know how to do that yet? By hand? No. Not a trick question. We haven't talked about how to do that by hand. The good news is we have Graphing Calculator, and Graphing Calculator can do that for us. So we'll get to that after we talk about the... do you want to just see it now? Yeah, okay. Okay, so if I were to call this big F of x, okay, so now I've defined it as a function, okay, I could do a few things, right? I could say graph it, whoops, right? And it will. So the black is the graph of this accumulation function, okay? And I could also ask Graphing Calculator to tell me what is the value of f of 1. And it will tell me. So what this 120 is representing is the total accumulation for this rate of change function, the t squared minus 3t plus 7, starting at -5 and ending at 1. Okay? So Graphing Calculator can do all of that for us. Okay, so cool beans. Let's see what else we got. So for this second integral, is this a valid expression? Yes or no? No. Shelly, you said no? Why? So there's a variable mismatch inside of our expression, so that I've got a w here and a t here. So I need to pick one and stay consistent with it. So what would you like the variable to be? Let's change that to a w. And now this expression is valid, okay? And is it going to produce a value or a function? Oh, so a value is a number, right? When you get an actual numerical value, versus a function is when you can change, you can change an input. So like we had up here, so I can plug in different values of x, right, and let x vary, and that will actually give me a function, right? As opposed to if I notice, so I showed you what it looks like using function notation when I do f of 1, but I could also have just placed a 1 there, right? So that's what we were doing when he said f of 1. F of 1 means plug in 1 for x. And when you do that, from -5 to 1, the accumulation is 120. That's a value, okay? So this outputs the value when I put the 1 in the top, okay? Did that clarify? I think some people just, the light bulb went off. Was that good? So, so what I've got written here is the same as what I computed when I wrote f of 1, because I plugged in 1 for x. Yes?
So does it depend on whether the top value of the integral is like x, or if it's like a number? Then if it's an x, then it's a function, and if it's a number, then it's a value?
I don't want to say universally yes, because there are things where you can have the x on the bottom, right? And that'll still give you a function. So like I could have the x down here.
So if both of them are numbers, then?
Yeah, if both of them are numbers, you'll end up with a value. Okay. Okay, so let's move down to this one. So we fixed that one. We're going to get a function out of it, and it's going to give me the total. Oh, question? Mm-hmm. Right. Are you talking, so, okay, so I like where your brain's at, and I need you to be more specific with your question, because we've got lots of functions running around right now. This one? Yeah, which I can't figure out how to put back in there right now. Okay, hold on, let me fix it, because okay, Control-Shift-I. Control-Shift-I gives you the integral, okay? So we went from -1 to 5, whoops. And do you want to know, okay, say it again. Okay, so when you say plugging it into our equation, we need to be careful about whether or not we're talking about the rate function or the accumulation function. The rate function. Okay, so let me define r of x to be x squared minus 3x plus 7. Okay, and so you're asking if we do r of 5 minus r of -1, we don't get the same thing. Okay, so why is that? This is a very, I mean, so this is a legitimate question. You guys have the answer to it. So take a second to think about it, because you have the answer. Think about, what does this mean versus what does this mean? All right, Elena, are you here? Elena? Elena? No? Yes? No? No, Elena. Jessica? Sutton? Hi. So what does this top expression represent? What does it mean? Okay. Okay, so this is a total accumulation from -1 to 5 if our rate function is t squared minus 3t plus 7. Okay. Joseph, what does the highlighted expression mean?
That's your change in your rate when your rate function has an input of 5 and -1.
Okay, so that's representing a change in rate. Exactly what you said. So is a change in rate the same as a total accumulation? No, those have different meanings, okay? But what we could do to create something equivalent, because you're right, there is something equivalent. So if I want to talk about an accumulation though, okay, I have a way to define an accumulation function, right? So this is a value, what's highlighted, but that came from a function, right? My accumulation function. So if I were to want the total accumulation from -1 to 5, then what could I do using this accumulation function to produce that value? Should we do baby steps? So A of 5 will give me the total accumulation. In this case, I chose to start at -10. That was an arbitrary choice. Just picked it randomly. Okay. So the total accumulation from -10 to 5. Okay. But I want the total accumulation from -1 to 5. So I could subtract the total accumulation from -10 to -1, and that difference will leave me with the accumulation between -1 and 5. Is the -10 annoying? You want it to just be -1? Since we're thinking about starting at -1? Yeah, okay. So imagine that you have, so if we were to start at -10, okay, then you're accumulating from -10 up until 5, right? But you only want the accumulation between -1 and 5. So if I have the total accumulation between -10 and 5, and the total accumulation between -10 and -1, then if I take this away from this, I get what I want. Like the hand motions? Should I draw? Should I? I know, right?
Relax.
Do you want a picture on the screen? Or, let me try. Okay, so we've got. So we're going to use bars to represent this, right? So from -10 to 5, I've got some accumulation. And then from -10 to -1, I've got some accumulation. If I take this piece away from the whole thing, then I'm left with this. Okay? So that's what we're doing when we do A of 5 minus A of -1. Okay? So A of -10, if I start at -10, how much can you accumulate if your x value starts at -10 and ends at -10? Nothing. You want to verify that? Because we can. Check it out. Look, look, look. A of -10. Nothing. Right? If you start at -10 and you end at -10, you have no opportunity to accumulate. There's no changes in x.
Okay, that's why we're not starting at.
Okay? All right, let's keep. Oh, question?
Could we rewrite the integration to be the x value being, what do we say we were starting, ending at 5, and then could that -10 be -1? Could that be the same thing as saying a of 5 minus a of -1?
Yes. So what I had here, A of 5 minus A of -1, is the same as if I start at -1 there and go to 5 there. Now if I erase C. Okay. Whoa. Ignore. Okay. So let's move forward. Okay. All right. So then we fixed this guy. What about this guy? The third one. Is this valid or invalid? Oh, wait. I just heard the valid. Was that valid or invalid? Invalid. Valid? What is it? So my ending value cannot be the same as the variable that I use inside of my integral expression. Okay, so one of those guys has to change. This one's highlighted, so I'll change that one. Okay. Are we okay with the fact that what kind of rate function is this? Well, it's a constant rate. What kind of accumulation function is this going to be? Test on Thursday. If you have a constant rate of change, what kind of accumulation function do you have? A linear accumulation function. That's how we built it up, remember? Constant rate of change gives you piecewise linear, so step constants gives you piecewise linear. Well, if the whole rate of change function is just a constant, that means you got one piece, right? One step. So one linear function for your accumulation. Okay? What about this guy? Question? Answer. Oh. Yes. You mean the fact that there's no x in there? So that's fine, because this is just a constant function. Okay? You don't have to have, right? You can, a function can be constant. So if I wanted to, my rate of change function here would be r of x equals e. That's my rate of change function for this integral. So it's a constant rate of change. The corresponding accumulation is going to be a linear function. Okay? All right. Fourth guy. Is good, right? Don't let the A distract you. Okay? A is just we've been using A as our starting value, but it's not delegated there forever, right? You can use it in other places. It's not conventional, but it's allowable. Okay? Question. Ah, is that okay now? That is no longer okay. Yeah, because now we're abusing A, right? We're using it in way too many ways. Okay, so no. Okay. All right. Down here. Oh, you have the answer. Is it valid? Yeah. Is it a function or a value? It's a value, right? You know it's valid because graphing calculator spit out something, right? Graphing calculator will only spit out something if what you've written is mathematically valid. Oh, so how does graphing calculator treat letters at the beginning of the alphabet? They're parameters, right? And what does it automatically assign values? What's the automatically assigned value to a parameter? 1. So this expression, as written in graphing calculator, is really being read as this. Okay? Now, if there weren't, if I wasn't in the graphing calculator environment, and you couldn't see that, right, then this would, in fact, be a function. It would be a function of, is it a function of x? It's a function of a, right? Question?
As far as the test goes,
yes.
do you have someone that on the test who wants to treat it like it is in graphing calculator, or it's just standard?
I will be very clear. If I'm asking you stuff about what graphing calculator would do, you will see. In graphing calculator, what would this look like? Or what would this produce? But if you don't see that phrasing, then just don't think about graphing calculator.
Graphing calculator assigns a value to letters from A to what?
Oh, I don't know. I think it pretty much assigns values to any letter other than the reserved ones that we talked about at the beginning. So like X, T, those are safe, right? N is reserved as a slider, but like A, B, C, some of those. Okay. All right. Now, so here's the thing. You're going to start having homework soon that's going to ask you to do things with integrals. We haven't talked about how to compute them by hand, so you're going to use Graphing Calculator to do that. Okay? So Control-Shift-I makes an integral. Control-Shift-I. That's how you're going to get through it. Okay? Now, I've got 5 minutes. Oh, no. To talk about a really cool thing, which is the fact that, we don't have the tools yet to do things by hand, but what that allows us to do is use Graphing Calculator while we concentrate on the meaning of what we're doing, okay? So I've got a nifty problem here where we've got a malfunctioning refrigerator. Ooh, boy. Hope it's not July. Okay, so then, so here's the rate of change function, and this screen right here, right? And we want to do a few things. So because we're a little bit short on time, maybe let's concentrate on the first 2 questions for now, okay? So talk to your neighbor, try to answer these first 2 questions. Make it bigger? The graph? Sure. Is that what you mean? Oh. No, I don't think so. Sorry. It is, yeah. So it's the 2, 4, 6, 8, 10. Yes. That's what we're trying to figure out, right? All right. Because we're short on time. Oh, I hate to interrupt because you guys are having such good conversations. But let's talk about it. So what's happening over the first 15 minutes? So like, I don't know, what's going on? Where should I look? How should I parse this? Is it is the temperature decreasing, then increasing, then decreasing? Oh, no, right? Because this is the rate function. So the fact that it goes down and then up, that has nothing to do with the temperature increasing or decreasing, right? Instead, we focus on the fact that the rate of change is negative here, right? So from 0 to almost 4 minutes, what is the temperature doing? It's decreasing because the rate is negative, okay? And then the rate is positive, so then the temperature is going to increase from about 4 minutes to about 13 minutes, okay? And then for the last like 2 minutes, it's decreasing again, okay? So then were you able to estimate about when during the first 15 minutes the temperature returns to its starting value of 40 degrees? So remember, because it's decreasing and then increasing. So it dips down below 40 and then it goes, and then it starts to increase again. So about when would it get back to 40? Maybe around 7 minutes, so maybe around here, 7 minutes. Do you have a way? How did you think about that? So like it's decreasing fast and then slower, and then it's increasing slower and then faster. So it's sort of like this not necessarily mirror image, but like opposite forces kind of thing going on. Okay. Should I make the last 3 homework? Or do you want to talk about them? We're kind of done with time. What do you want to do? Wednesday? Mark will take care of it on Wednesday. All right.